If you have a strong, the equivalence point is going to be pretty much strong is going to be 7. But if you have a weak acid strong base, the equivalence point is going to be slightly basic. If you have a strong acid weak base, Today we're going to talk about titration curves in various combinations of acids and bases, strong or weak, and qualitatively understand the differences between them. We're going to start off with drawing a beaker, and let's suppose we put the acid in the beaker. Let's suppose we put the base in the burette. And we have different possibilities for these. We could have a strong base or a weak base. The strong base would be something like NaOH. The weak base would be something like NH3. We could have a strong acid or a weak acid. The strong acid would be something like HCl. The weak acid would be something like acetic acid. So these are going to look differently in their titration curves. Let's just mark down the 7s here roughly in the middle of a pH and discover again how they relate, how the equivalence point relates to that. So if you have a strong, you're going to start off very acidic and you're going to end very basic, and your equivalence point is going to be 7. If you have a weak acid, you're not starting quite as low, but you're ending fairly high with the strong base, and so your equivalence point is going to be above 7 or basic. If you have a strong acid and a weak base, we saw that the equivalence point is going to be slightly acidic. And if you have a weak, it gets kind of complicated. I'm going to draw it as 7 here simply because we're using, in my example, ammonia and acetic acid, which have the same Kb and Ka values. So because they're exactly equal, this equivalence point will be 7. But if one of them has a higher Kb or Ka than the other, then it skews the equivalence point slightly. So this procedure that we're going to follow with figuring out the pH at every possible point on the titration is going to stem and flow out of what we learned with buffers. So in the very beginning, you're always going to have the acid by itself. Here you have a strong, here you have a weak. So if you have a strong, the acid by itself is going to be a molarity equals moles over liters. If you have a weak, you would do ice and Ka. That's the acid by itself right here before you added any base. As soon as you add some base, remember you ask yourself, is there a reaction? And the answer is always going to be yes, because we have an acid and a base going together. And so you're going to do the classic stoichion moles. So you do stoichion moles, limiting reagent, and one thing is going to run out in the calculation. The equivalence point is when the moles of acid and base are exactly the same. That's the very important part of a titration, which we saw through the labs. That's what we're trying to find to discover the missing molarity. So regardless, whichever point of the titration you are ending, the final line of your stoichion moles is going to tell you what you have left. Do you have a strong, do you have a weak, or do you have a buffer? And you're going to apply the appropriate calculation for that. A special point in a titration is called the halfway point. This is only going to be important really when you have a weak acid or base in the titration. The special situation is the H plus will equal the Ka, or the OH minus will equal the Kb for a weak acid or base. So it has to be weak for this halfway point to really be relevant. We'll see all this in the next couple of slides. We are on page 6 of the AP Chemistry Chapter 15 packet, and we're going to be discussing the titration curve of a strong acid and a strong base more quantitatively right now. So to start off, let's review what our titration curve is going to look like. If this is 7, remember that if we're going to put an acid into the, in this case, Erlenmeyer flask, and a base into the burette, we're going to see that we're going to start off with a pH that's very low, because we're starting off with a strong acid, and then we're going to end very high because we're ending with a strong base, and the equivalence point is going to be 7 because it's going to be a strong versus a strong. There are 4 main parts to a titration, and one of the most important parts is the equivalence point. So let's talk about that first. The best thing to do is find the equivalence point. Like, you figure out what volume of NaOH has to be added, and that's going to go right over here. Okay, that's going to be the equivalence point right there. So how do we figure this out? We look at what we know. We know the molarity of the acid. We know the volume of the acid. So we could find the moles of the acid. You could actually also work in millimoles if you prefer. So here's that setup. If you have 30 milliliters, then you could solve for the millimoles, and that comes out to be 60 millimoles. So this is the same as that. Now remember, when you're titrating these two, they react in a 1-to-1 ratio. So those moles are going to be the same, 60 millimoles, all right? And that's going to be a volume of 15 milliliters. So you're going to need 15 milliliters of this base to titrate to the equivalence point. So it's going to be 15 right here for the base. There's another way to figure this out. So this way is pretty much foolproof as long as you can make the connection of, like, if this were CaOH2, then you would need half the amount of moles because it's, you know, going to give you twice as many. There's another formula that you could use, which is normality of acid times volume of acid equals normality of base times volume of base. And now you're going to say, well, what's normality? Normality specifically is for acids and bases, and it's equal to the molarity times either the number of H pluses for an acid or the number of OH minuses for a base. So I'll give you a few examples. Let's suppose you had a 0.1 molar and a HCl. 0.1 molar HCl. There's only one H in that, so that means that you're going to have 0.1 normal, because that is going to be the molarity of the H plus. It's really that you're looking for the concentration of the H plus. So let's say we had a 0.1 molar H2SO4. This has two H's, so you'd have to double the molarity to know the normality. All right, let's move on to take a couple of bases. So let's say we had NaOH, and let's change it up and make it a 0.2 molar NaOH. That would be a 0.2 normal NaOH as well, because it's going to have only one OH. But if you had a 0.2 molar calcium hydroxide, which has two OHs, that's going to be a 0.4 normal CaOH2. Okay, so now we're going to move on to do our calculation and show you how that works. Unfortunately, that is not moving. Let's do it for this calculation right here. So the molarity of the HCl is 2. So the normality is also 2. So 2 normal. The volume, you can use milliliters, 30 milliliters. Now we're going to know the molarity of the NaOH already. It's given to us, so the normality is also 4 normal. And then we could solve for the volume in this case, which is 15 milliliters. So I'm just showing you a couple different ways to get the equivalence point. One is to just do molarity equals moles over liters, copy down the moles, solve for the volume. Another way is just to do the NAVA equals NBVB calculation. Either way, we found out that the equivalence point happens at 15 milliliters for the NaOH. So if I said find the pH at the 4 main parts of this titration, the 4 main parts are going to be the beginning, halfway point is usually exciting, equivalence point, and then somewhere past it. So there's 4 main points. If we look at these 4 main points, we're going to see that the first one is the initial concentration when you only have H plus in here by itself. As soon as you add some of the NaOH, it's going to react, and you're going to have stoichiomoles from that point on. So let's take one at a time. Let's take the initial. Here's the initial. So if I tell you you have 30 milliliters of a 2 molar HCl, what's the pH? You just say, oh, it's a strong. So I do moles over liters, which is still 2 molar, and I take the negative log, I get negative 0.301. So that pH is going to be negative 0.301 right here. Negative 0.301. Then let's add a bunch of NaOH. Let's make it the halfway point. The halfway point is going to be halfway to the equivalent, so this has to be 7.50 milliliters of NaOH. So now we're going to go back and do our stoich in moles. Let's move this up a little bit. So here's our stoich in moles. We have 0.060 moles. I did moles instead of millimoles here, so this is the HCl. Now if I only added 7.5 milliliters of a 4 molar, I got 0.03 moles. So you can see that this is going to run out, and I have O3 left over, and I made O3. This is water. It's not really going to affect anything. I have 030 moles of H plus left. So what do I have? I have a strong. So I only have a strong acid now. So whenever I have a strong, I'm going to do moles over liters. And of course here I also had a strong, so I do moles over liters, and I'm going to get the molarity is 0.8. That's because I had to add the total volume. This is tricky. I added 7.5 milliliters to my original 30. So 30 plus 7.5 is going to be 37.5 liters, 0.0375 liters. Negative log, there it is, 0.0969. Okay, so this pH right here is going to be 0.0969. Do that over there, 0.0969. Okay, we move on to the equivalence point. That's when I've added exactly my 15 of NaOH. And when you do the math, you're going to note again that these moles are going to match these moles, so they run out. And all I have is water, and so I just take the negative log of that, 10 to the minus 7th, I get 7.00. Now let's suppose that I go past the equivalence point. So now I'm adding 16 milliliters. Remember the equivalence point came at 15 milliliters. So now I have too much NaOH. I went past the equivalence point. Well, here's the moles. So these moles run out, and I have leftovers of this, and then you have to ask yourself, well, what do I have? I have a strong base. So how do I handle a strong base? I do moles over liters. So my moles is 0.004, but my liters is the total that we got from adding 16 milliliters to my original 30. So that's going to be 46. Negative log, and you get pH of 12.85. Now on the next page is a you try it. I'd like you to try it by yourself, but I'm going to do a video of it just in case you have trouble. Actually, one more thing to mention on this video before we turn the page. I just wanted to put this 12.85 up here so you could see it. So the pH ended up as 12.85 right here, and you can see that that's quite a big jump, and that's because you have extra NaOH, and so you went from 7 to 12.85 pretty drastically in only 1 milliliter. And you saw this happen in your lab, your titration lab as well, where there was a very sudden change in pH when you're close to the equivalence point. This would be 5. And then I should have said before to do 1 milliliter past the NaOH, like beyond the equivalence point. Okay, so let's take a look and see what we got. We're going to start off with the acid by itself in the flask. When you have an acid by itself, in this case, you ask yourself, what do I have? A strong, weak, or a buffer? I have a strong acid. Since I have a strong acid, I do moles over liters, which is still the same molarity. So it was a 1 molar. I haven't done anything to it yet. This is like sitting in the flask. So it's just a 1 molar, and it's strong. So it's the same as the H plus, and then you take the negative log of that, and you get 0. So this starts off with a pH of 0. Now the halfway point is when we've added 5 milliliters of the NaOH. So I know that I started off, no matter what, with 0.040 of the acid. That's like already there. Okay, so this is always going to be 0.040 in this whole problem. 0.040. Then I'm going to solve for the moles of the NaOH. Since I added 5 milliliters, I'm going to write 0.005 liters here. And that means that I added 0.02 moles. So the running out, the limiting reagent is going to be the 0.02. So write this minus 0.02 minus 0.02 plus 0.02. And when I'm all done, I have 0.02 of this, none of that, and 0.02 of this, but that's water. So look at what I have, 0.02 moles of H plus, that's a strong acid. How do I handle a strong acid? Moles over liters. So I simply take my moles, 0.020 moles. I need the total volume, which means I added 0.005 liters to my original 40 milliliters, which is 0.04. So the total is 0.045 liters. That molarity is going to be 0.44 molar, and the negative log of that is going to be 0.35. So now this pH is 0.35. So you can see the halfway point is not really that much higher than the beginning. However, when you get to the equivalence point, that's when things really change drastically. So let's go to the equivalence point. I know that I've added 10 milliliters of the base, so I'm going to write my 0.010 liters here. And remember, I already knew that this was 0.040 for the acid moles. And of course, at the equivalence point, this should come out to be the exact same number. So then when you do your stoic in moles, because there's a reaction, you're going to subtract the 0.040 from each one and add it to the water, which won't really matter, of course. So that's 0.040. That's going to be a 0. That's going to be a 0. What do I have left? I just have water. So clearly the H plus is going to be 10 to the 1.010 to minus 7th. And when you take the negative log of that, you get 7.00. Now let's go 1 milliliter past the equivalence point. 1 milliliter past. So instead of adding 10 milliliters, I've added 11 milliliters. So, sorry about that, 0.011. 0.011. So that's going to give me 0.044 moles. Again, I had already started at a 0.040 moles. So the one that runs out is now the H plus, which makes sense because I went too far in my titration, or past the equivalence point, I should say. And so this is a 0. This is a 0.004 moles, and that's 0.040 moles. And now I look at what I have just OH minus. OH minus by itself is a strong base. How do I handle a strong base? I do moles over liters. So it's 0.040 moles divided by the total volume, which is this 11 milliliters plus the original, which was 40. So 40 plus 11 is 51. So 0.051 liters. The molarity comes out to be 0.078. Now remember, that's the OH, so you have to negative log and then 14 minus. And when you do that, you get a pH of 12.89, which is, of course, very basic. There was the molarity before. So if we go up here and label 12.89, we'll see that that's much, much higher than we started because we ended with a strong base. So we had a very high pH. Okay, so remember, 4 main parts to a titration. You can identify them easily. They're going to be the beginning acid by itself, halfway to the equivalence point itself, and just past the equivalence point.